Okay, so to find zeros and analyze polynomials, we're just taking what we're doing with polynomials a little bit further. We're still going to use synthetic division, but we'll look at some fourth degrees polynomials also here. So for the first one, and this is from the note sheet, we're asked to verify that -7 is a zero of the polynomial p of x, or f of x actually, x to the fourth plus 6x cubed minus 17x squared minus 78x minus 56. Okay, so with this, we're going to do synthetic division, right? We should see a remainder of 0, or else we didn't confirm it's a 0. But when we get our quotient, it's going to be 1 degree lower, correct? It's going to be degree 3. So let's see how this looks. So we'll put the -7 up in the box. 1, 6, -17, -78, -56. Okay, and then the synthetic division, it worked, I hope. So we get 1, -7, -1, 7, -10, 70, -8, 56, 0. Right? Synthetic division worked. Now at this point, I would like you to rewrite f of x as x plus 7, right? If -7 was the 0, because we had a remainder of 0, it's a 0. The associated factor is x plus 7. And then we know that this quotient here is going to be cubic, right? We had a fourth degree, we knock it down to cubic. So we'll get x cubed minus x squared minus 10x minus 8. Now at this point, you know, if we were going to graph it, we know there's one x-intercept at -7. There's probably some here. If you tried to factor this by grouping, it doesn't work. Like it's not going to group nicely. Does everybody know what I mean by that? When I say by grouping it wouldn't work. Those two parentheses have to match. Real quick. What I mean there is if this looks like, you know, there's no common factor, but if I take the first pair, you get x minus 1, and then -2, 5x plus 4. For grouping to work, these two have to match. If they don't match, and it's not a case where maybe like, oh, take out a negative or something, then it just doesn't work. So what we have to do here is we want to determine the next kind of line here is that determine if 4 is a 0 of the resulting cubic polynomial using synthetic division. So the next question is 4 a 0 of the quotient? And what's going to happen is we look at higher degree polynomials, fourth degree or larger, is the first synthetic division won't get you, because we can solve quadratics, right? We're great at quadratics. But we're not really good at this yet. So what we're going to do is now we're going to do synthetic division on this quotient, which is degree 3. So if we find a 0, its quotient will be degree 2, correct? And once it's degree 2, then we can do our factoring stuff. So what we'll do is we're going to do 4 in the corner, and then 1, -1, -10, -8. We get 1, 4, 3, 12, 2, 8, 0. So was it a 0? Sure. And if it's a 0 of the quotient, it had to be a 0 of the original. So now at this point, this is really important to write. It'll really help us kind of keep what we're doing straight. Is f of x, the original polynomial, has a factor of x plus 7. It has a factor of x minus 4, right, because we know those are both zeros. And then it has x squared plus 3x plus 2. Well, that's really nice, right? Because this is factorable. So we factor that. We get f of x equals x plus 7, x minus 4, x plus 2, x plus 1. I can't recommend writing this factored form each time enough. Like, it will keep you from losing stuff. It's real common with this type of problem. If people don't write this step out, they forget that -7 is a 0. Because the question will say list all zeros. You list them all even if you were told they're a 0. So in this case, we would say that we have zeros at -7, 4, -2, -1. Or if we used our graph, our x-intercepts would be at -7, 0, 4, 0, -2, 0, -1, 0. Right? And with these, with our initial information, we could sketch that, right? We could sketch this 4th degree polynomial without too much trouble. Okay, so this is our rational zeros theorem. I guess we could give it a name, right? Rational zeros theorem. And this is how we're going to get a list of potential zeros from our polynomial. Okay, so it's pretty amazing that it works, I think, when you consider all the different possible, and we're even going to get fractions and stuff. But with this definition, just a few things to note, to be aware of. So if the polynomial p of x equals, again, it's this big expanded form, right? A sub n is the leading coefficient, a sub 0 is the constant term, has integer coefficients. So integer is a positive or negative counting number, correct? So that means all of these a's will be whole numbers or negative whole numbers. There won't be any fractions, right? So if you had a 1/2 x cubed in there, this wouldn't work. Now later on we can see how we could kind of force it to work, but that's something important to note. But then every rational zero of p has the form p over q. A rational zero is just a rational number, and a rational number is one that can be written as a fraction of a whole number over a whole number. Okay, so every fraction is a rational number. Every repeating decimal, like 0.3 repeating, is a rational number. Every repeating decimal, right, or terminating decimal is also rational. The things that are not rational would be like the square root of 5, like we saw an example earlier, right? That's an irrational number. The number pi is irrational. The number e is irrational. Those never show up. It's mostly just means square roots for our purposes, right? This will list every zero that doesn't have a square root in it. That's kind of how we can think of that. It has the form p over q, where p is a factor of the constant term, a sub 0, and q is a factor of a sub n. Now this is not factoring at all. This is just saying what numbers go into. Like, 10 has the factors 1, 2, 5, and 10. Right? Or 8 has the factors 1, 2, 4, and 8. The numbers you can multiply to get that number. So for our first example here, we have p of x equals 3x cubed plus 4x squared plus 6x minus 5. So the possible rational zeros. So we know that p, those would be our factors of -5, correct? So our value for p, our p values would be the factors of -5, which would be 1 and 5. Okay, q would be the factors of 3, which would be 1 and 3. So now we're going to make all the fractions, so our possible rational zeros would either be, you take each of the p numbers and put them over each of the q numbers. So it could be 1 divided by 1, which is 1, 5 divided by 1, which is 5, 1 divided by 3, which is 1/3, 5 divided by 3, which is 5/3. Now, because rational numbers can be positive or negative, we also have to consider the negatives. So typically what I do is write them out like this, and then put them all in a parenthesis and put plus or minus out in front. To remind myself, it could be 1 or it could be -1. It could be 5 or it could be -5. So as we look here, our list contains 8 numbers, correct? 4 positives and 4 negatives. So that's really powerful. If you're trying to find the zeros of this polynomial, right? If there is a rational zero, it has to be one of these 8 numbers. So what we're going to do next time we're together is we're going to look at we just start using synthetic division until we find one that works, right? Until we get a remainder of 0, and then we can factor it the rest of the way. Okay, so that was our rational zero theorem. So if you would, maybe try this next one, which is, well, go ahead and try the next one. So here is the second example. We have p of x equals x to the 4th minus 5x cubed minus 5x squared plus 23x plus 10. So again, none of this, in terms of this part, none of the middle stuff matters, right? We're just looking for our p's and our q's. So again, p's would be the factors of 10. So that would be 1, 2, 5, and 10. And then the q's would be factors of 1. It's always nice on these when you get the leading coefficient as 1, because it means you're not going to have to try synthetic division with any fractions. Now, it looks like it would be scary to do synthetic division with fractions, but usually you tell right away if it's going to work or not. Like if you get terrible fractions, it's not going to work and you stop. So we'll deal with that tomorrow. So with this, our possible rational zeros, plus or minus, right? It could be positive or negative. We just take all the p's over 1, so 1, 2, 5, and 10. Right, so again, there's 8 possibilities. Now, just to be clear, these are just possible, right? They all couldn't be zeros, or, you know, it's only a 4th degree polynomial. Most it can have is 4. So they can't all work. It could be that none of them work. We have no idea until we test them. But if any rational number works, it's going to be from this list, which is powerful, right? Because if you think about it, there's an infinite number of rational numbers between 0 and 1. You know, 1/2, 1/3, 1/4, 1/5, 1/6, 1/7. Like, this is 8's a lot smaller than infinity. Even though if you take an 8 and you turn it sideways, it looks like an infinity. That's completely unrelated.